Today is February 15th, 2012, and this is AP Statistics at Berkeley High School. So in Chapter 11, we're going to develop ideas revolving around distributions of categorical data. Now typically what we've been saying is that categorical data, we've been treating like a proportion problem. And if you're in one category, we call that category the success. If you're in some of the other category, we call that the failure. But we know that categorical data actually falls into different categories. For example, how many different eye colors can you have? There's blue, there's brown, there's green, there's hazel, there's black. Which one is the successful category? Only blue eyes? Only black eyes. Or, in my case, red eyes. There's lots of categories. Why does one of them have to be the successful category? Why does only one have to be the good category? So we're going to look at categorical data, but we're not going to impose the binomial nature of categorical, good and bad, successful or failure. We're going to do the analysis using these multiple categories, using what's called chi-square goodness of fit. And also we're going to be looking at relationships between categorical variables to see if there's a dependence or lack of independence between those variables. Inference for relationships, that'll have to wait until 11.2. So, in this section, we are going to start by being able to compute what's called expected counts and the conditional distributions, the things that make up what's called the chi-square test statistic. We are going to look at. We're going to look at the conditions in which we have to meet in order to do the chi-square analysis, random. We're going to have not the normality check that we've been so used to, but something called a large sample check, and then also check for independence. We are going to perform the chi-square goodness of fit test on data today. And then we'll look at what's called the individual components that make up the chi-square analysis so that we can say, if there is a significant difference, where's that difference coming from? So, let's start. So, in the previous chapter, as I said before, we've done things where we look at categorical data, but we've always put it into two groups, success or failure. Okay? Today we're going to look at multiple groups simultaneously. Okay, we can decide whether the distribution of categorical variables differs Am I in the right section? Because this is talking about test for homogeneity.
That's what it says in the book.
No, but the first section should be on goodness of fit. Oh, I'm sorry. This is a big overview of the whole chapter. I'm sorry, I got sidetracked. Today we're going to be looking at this particular area. This particular area is the 11.1 area. The test of association, independence, and chi-square test of homogeneity, that's the stuff we're going to be looking at 11.2. I'm sorry. I just saw the homogeneity. I'm like, I'm not ready to talk about that today. So, today we're going to look at something called the goodness of fit test. Okay? And then later we'll look at relationships between two categorical variables, and that's going to be the test for homogeneity, test for independence and association. All right. So, here's what we've got. Candy company, Mars, creates milk chocolate candies. Those candies are known as M&Ms. In fact, I happen to have a sample of M&Ms right here. On average, they make these candies so that about 13% of the candies are brown, 13% are red, 14% are yellow, 60% are greens, 20% are orange, and 24% are blues. I would call the colors for the distribution of those candies, I would call them categorical. All right? Let's say we took a sample of M&Ms. Oh, look at this. I have many samples. I probably have one sample for each of you. This one's Michaela's. Michaela, get ready. Okay. What's that? Okay, this one's for Emily. Emily this time. Okay, one more time. It's not about the strength. It's about the no. No, that wasn't any better. Ready? Oh, that was the best throw of all. Okay, here we go. Ready? It was much more about her catch than it was about my throw. Okay, who hasn't got him yet? Okay, Sam. Off the wall. Paul. Nicole. Okay, Jessica. Alyssa. Nolan. Gotcha. Becca. And a little off. Okay, right? Oh, okay. Has everyone got a packet now?
No, I need one.
Where are you, Kyle? All right. All right. So each of you have a sample of M&Ms. Now, every one of these samples can compare to what we expect to be the distribution of M&Ms. Now, I'm going to do this once, and then after I do it once, you're also going to do it, and we're going to go through the analysis. All right? So let's say I break open my sample. All right? And of course, my categories are those different colors. All right? So I'm going to break open my sample, and I'm going to count up the number of yellows. Or actually, what do they want first? They want blue first. So how many blues do I have? I've got 2, 4, 5. I've got 9. I've got 9 blues. Wait, I'm supposed to right click on. Wait, I'm supposed to right click on this. No, what's it say? It says, oh, control click. Oh, sorry. The reason why it's not working is because I need to be here. I can go to my sheets. Okay, so I observed 9. That was a coincidence that those were the same. What was next? The orange? No, I'm only seeing 7 orange in my bag. All right. Let's see. Green. I got a lot of green. So 5, 10, 12, 13 green. And in the yellow, I have 5, 10, 11 yellows. Reds, I have 5. And then in the browns, 5, 8. I have 8 browns. All right. Okay, so there's my particular chart. There's my particular chart. Blue is what I observed. Red is what I expected. It looks like I got shorted some blue M&Ms. Looks like I have an excessive number of green M&Ms and yellow M&Ms, as those observed columns are a little bit bigger. And look at this, my browns. I had 8, but I expected 7. I'm only just a little bit off on my browns. What if someone had broken into the M&M factory, fiddled with the knobs, made the distributions of colors different than what they should have been? Is this bag of M&Ms evidence that someone has screwed something up? Or is the fact that I didn't get exactly what I expected, is it just part of the chance variation of things? In other words, is this significantly different than what I expected? Is this not by pure chance alone? Or is this just part of the natural variation that goes on and nothing special is going on? Well, what we need to do is we need some sort of measurement of unusualness. A measurement of how far away are we away from what we expected. Now, I don't think I'm going to get exactly what I expected. I think it's actually impossible to get exactly what I expected with these M&Ms. Now, why is that? I'm going to go back and leave this one more time for a second. And I'm going to double click on this so you guys can look at the data sheet. Okay, although it doesn't show up, can you see that? Can you see I typed in 9, but above it the expected was 12.72. I was supposed to get 12.72 blues. Why is that? How did they come up with that number? The average? 24% of how many candies I had. So if I counted up the number of candies I had, 7 and 13 is 20, 29. 29 plus 11 is 40. 40 plus 5 is 45. 45 plus 8 is 53. So if I had 53 candies, and I expect that 24% of them are supposed to be blues, is 24% of 53 12.72? Oh, okay. So the expected number is this fractional number, and there's no way to get exactly that number. Wait, so, okay, no way to get exactly the number I expected. So everything is going to vary at least a little bit from expected. I guess the next question is, how do we measure how extremely different we are from what we're expected? Are we just a little bit off? Or are we a lot of off? In some ways, this is the stuff that we've been doing for the last 3 chapters with the Z and the T statistic. When our Z statistic was really close to what we expected, we would get numbers like Z equals 0, or Z is equal to 0.4 or 0.7. But when we were very far away from what we expected, we would get Z values of like 4 or 5. Same thing happened with the T values. We get really big T values, either really big negatively or really big positively. But we get really big T values or big Z values, and we'd say, oh, something special is going on here. The test statistic, the measurement of unusualness, is really, really high. Now, we didn't use those words, but it's indeed what we meant. And we did that for means, we did those for proportions, where categoricals only fell into one of 2 categories, yes or no, success or failure, Democrat or Republican, boy or girl, heart attack, no heart attack. All right? Let's take a look at trying to do an analysis of all of these things and try to get a number that represents the unusualness of our data set. Okay, so back here. We are going to describe our data in a one-way table. There's only one categorical variable going on here right now, and that categorical variable is called color. All right. I think on this one, can I edit this? I don't know if I can edit this. How many blue did I have? 9? Oh, that's not what I wanted. 9. How many orange? 7. Yeah, I don't think I can edit this on the fly. Green was 13. Yellow was 11. Red was 5. And brown was 8. For a total of 54. 54, 53. 53? 53. All right. So, if that's the case, the sample proportion of blue M&Ms, in my case, is indeed 9 divided by 53, giving me a sample proportion for blue M&Ms of, someone with a calculator, come to my rescue, please. Come on, I gave you candy. What's that? 0.17. Great. Okay. Come on. Now, with that p-hat value, I could test the claim. Do I have a significantly different number of blue M&Ms than I expected? And we already know how to do that. It's called a one sample or one prop z-test. We can compare it to our claim that the population proportion is 24%, and then we ask, is our sample proportion of 17% very, very different? We can run that test. That wasn't last chapter, that was 2 chapters ago. All right? And that's great. Could I do the same thing and then do it again with the yellows? Do it again with the oranges, and do each one of those tests individually? Yeah, but that's 6 different tests of proportions. I'm too old to do 6 of those one after another. I want to do all of them at once. So, although I could perform 6 one-sample z-tests, it would be inefficient. I would like one test to look at this data in its totality all at once. Let's see how that's done. First of all, let's give it a name. The name of what we're going to do is called the chi-square goodness of fit test. Now let's talk about the expression goodness of fit for just a second. It's goodness of fit because we have been told a model. We have been told that we should expect the distribution of colors for these M&Ms to have this particular percentages, 24% blue, for example. That's what we expect. We get data, and then we ask of the data, does this data actually match the model that was given to us? Is the model a good fit for the data? Or do we have evidence that someone broke into M&Ms and stole a bunch of green M&Ms? Because we know the green ones taste best. All right. Well, let's talk about more than just the name. Let's actually talk about doing it. Okay. First of all, because it's a significance test, we still have H0 and we still have HA. For the chi-square goodness of fit test, the H0 is always, the model is a good fit. Nothing special is going on. We have no evidence of the break-in to the M&M's factory. That the company's stated distribution for colors is indeed what's really going on. What would the H0 claim be then? Say it again, please. Sorry, I already said the HA. What's the HA claim? What's the alternate hypothesis? They're not equal. Something is not right. The model does not fit. That there is a difference. All of those things that sound somewhat similar to what we've done earlier. The H-dot claim in the earlier significance tests have been, nothing's gone on. This group is not different. The HA claim is, something is going on. Something is different. Same idea here, but now we don't have parameters. Now we don't have mu equals or p equals. We just have this over idea, there's a model. Either it is a good fit and nothing special is going on, it's not a good fit and something is special is going on. All right, so H0 and HA. By the way, are you following along on your scaffolding sheet? Okay, remember, yes. Oh, you didn't get one. All right. All right. And again, we're only doing the side that says goodness of fit today. All right. So, we could also write the H0 to say, oh, we expect the proportion of blues to be 24%, and the proportion of orange to be 20%, and the proportion of green to be 16%. And I'll probably keel over before I get to the end of that line. What I would tend to say is, what we're going to do, according to the sheet that we made for you to follow, that under the parameter area, in step 1, that's where we're just going to specify the model. We believe that we're going to have this many blue, this many orange. We specify the model there. And then we're just going to get in the habit of saying the H0 claim is, that model is correct. Sorry, I said that wrong, didn't I? Let's try that again. The H0 claim is, this model is correct. The thing that we specify in the parameter area. Our H0 claim, HA claim is going to be, something's wrong. Doesn't fit. All right. So we're not going to write it the way, we're not going to write it there. But take a look at the, if you use that alternate writing, take a look at the alternate hypothesis. At least one of these p's is incorrect. So we're going to have a test that even though we may have about the right number of reds, it's still going to be able to detect when there's too many oranges or not enough browns. We don't have to do 6 individual tests. We have one test that will detect that any of them are off. All right. So here's the idea of the goodness of fit test. We compare the observed counts to the expected counts. And from the difference between the observed and the expected, we're going to get a single number. And that single number is going to be representative of the unusualness of the data set. How far off are we from the expected? Okay? We're going to find that by multiplying the proportion of the population distribution for each category by its sample size. Let's skip over that for a second. I'm going to come back. I've got a great analogy that helps make that idea clear. So let's skip over that until I can, until we can do that. All right. Here we go. Let's take a look at the expected counts for each number. Now, at this point, I would like to have you have a sheet of paper in front of you. You've got your M&Ms. You're going to need a calculator because you're going to do with your own data what I'm going to do with my data. So each of you are going to end up with your own chi-square value that we can do an analysis with. All right? So go ahead. If you want, I've got some clean scrap paper for you to spread out your candies. Does anyone want to do that so that you maybe want to eat the candies when you're done? sure. Should be enough for your area. This should be enough for your area if you want to put it on. I would not put the candies on these desktops. I mean, people sneeze and ew. Oh, that was actually left over from math league yesterday. But grab a sheet, pass the rest back. All right. All right. All right.
No pun, man. You did it wrong.
Okay. Now, so you're sorting your candies on one fresh sheet of paper. In your notebook, though, here's what I'd like you to start writing down. I would like you to write down. I would like you to write down in a list the candy colors. And I wish I would have. Here, let me pull it up on my book. So I want to use the orders that we had in here. All right. So blue, orange, green, yellow, red, and brown. Okay, so there's our categories. Now what I'm going to do is I'm going to create a column, and I'm going to put the letter O at the top of that column. O for observed. Okay? And in my group, I observed 9 blue, 7 orange, 13 green, 11 yellow, 5 red, and 8 brown. Okay, obviously you're going to have different observed values than I am. But that column is called O for observed. Okay, now we need another column. And the next column we need for your sheet is E. E for expected. Now, we had already totaled up my numbers. It's 53. The question is, now, well, how many did I expect to be blue? How many did I expect to be orange? How many did I expect to be each of these colors? All right? So, let me write down those percentages so that we can do those calculations. We expected 24% to be blue. Now, that's a percentage. What I want over here is an expected count. I want to say if indeed 24% were blue, I would have expected 12.72 of them to be blue. And again, I'm okay with the fractions there. For the orange, we had said that we expected 20% of them to be orange. So 20% of 53, that's 10.6. I should have had 10.6 orange M&Ms. Can't have exactly 10.6, but I'm going to leave the 10.6 there. Okay? For the green, 16% were supposed to be green. So I asked, what is 16% of 53? And I get 8.48. Yep. For the yellows, as we said, it was 14%. So I go 14% of 53 is 7.42. For the reds, 13%. And for the browns, 13%. So 13% of 53 gets us 6.89. Right? And that's what we expected. By the way, if I total up this expected column, what number do I get? 53. Right? How many, by the way, did all of you get 53 M&Ms in your packets? 56? 57. So there's some variation there. Considering that M&Ms are pretty consistent, I would imagine that means that the weights of these packages aren't actually very consistent. But anyway, there's my numbers. You're going to have to do it with your numbers based on your total number of M&Ms. All right?
24% of 53.
So this number here is indeed 24% of 53. Each one of these is the total number of M&Ms multiplied by what the proportion that the model says it should happen. All right? And then I'm going to make another column. And that column is O minus E. Observed minus expected. So this first one's going to be negative 3.72. Let me just double check that. Yep. Oh, I'm sorry, not negative. Yes, negative. 9 minus 12, yep, negative. Okay, this one's going to be negative 3.6. This one is positive 4.52. So what does it mean that these values are positive or negative?
If it's negative, the expected value is more.
Okay, if it's negative, the expected value is more, meaning if it's negative, I didn't get as many as I expected. If it's positive, I got more than I expected. All right? So 11 minus 7.52. I have more than the expected number of yellows. I am short red. But maybe it's made up for the fact that I have more browns than I expected. Right? So now I've got O minus E, observed minus expected. Now, guess what happens when I add up this column? Indeed, I get 0. So the sum of O minus E is not a very good measurement of how unusual my bag of M&Ms is. Because you know what? If I follow this procedure every single time, I'm always going to get 0 in that column. And so are you. Can you confirm that? Did you calculate it? You really, I'd like you to. I was afraid of. So, O minus E, not a good measurement of how unusual the group is. So, what's wrong with 0? How can we get rid of the zeros? We could do absolute value. And, except for the fact the calculus part of the statistics going on in the background doesn't work well with absolute value, it would be perfectly fine. But we had the same problem way back in the first marking period when we first looked at standard deviation. And instead of using absolute value there, they did something called squaring it. So we've got this going on. We're going to take this value and square it. Don't do anything more yet.
You sound like residuals.
Well, the positive and negative values are like residuals, indeed. All right? By the way, you probably, once you get your counts down, you can start eating your M&Ms. It's okay with me. All right? Wow. Nate's only got 2 red M&Ms. Someone broke into the factory. All right. So, I got one more thing I'm going to add to this last column. All right? Who am I going to pick on? Nicole. I heard you're having a party. You say yes. Oh, I'm sorry. I said that wrong. Nicole, I heard you had a party. Last night. Valentine's Day party. You know what? I heard that Nicole invited 10 people over to her house for a Valentine's party. No, not me. I would invite me. All right? But then I heard the bad news. No, the bad news was Nicole, she invited 10 people over to her house.
No one showed up.
Only 5 showed up.
Oh.
Sorry, Nicole.
Bummer.
Paul, I heard you had a party last night too. Because we all know about Paul and his proclivity for Valentine's Day escapades.
They based movie Valentine's Day off me. Like the one that
Well, I heard that you had earned so many credits with Tri-M that they were willing to just play music all night long at your party, which is good because I heard you invited 500 people to your party.
That's impressive.
That is impressive. No, I heard that some people didn't show up. You know what? I heard that 5 people of the 500 people didn't show up. Okay, now let's compare Nicole to Paul for a second. She invited 10, 5 didn't show up. Paul invited 500, 5 didn't show up. Is there a difference there? Tell me about that difference. Is being off by 5 the same in every single context?
No.
In Nicole's context, it's a really big deal. In Paul's context, not a big deal at all. So, something about the size, not just the difference, but something about the size matters. And we're going to incorporate that idea by doing that. Nope, this is one. I'm going to do this in one big column. Yeah, they did it in 2. I'm doing it in 1. All right? Now, here's the idea. Because the size of the expected value matters in its interpretation, we feel very sorry for Nicole with her missing 5 people. We were like, Paul, you only missed 5 out of 500? That's incredible. Because the size of the expectation matters, we're not only going to square this value and get rid of the negative sign, we're also going to divide it by E to then put it in perspective. Nicole's missing 5 people would end up creating a really big value in that column. Paul's 5 missing people would create a very small number in that value. All right? So now that's what we're going to do. We're going to take the number in O minus E, we're going to square it, and then we are going to divide it by expected. All right? So I'm going to go ahead and start doing that. 3.72 squared divided by 12.72. And I get, in this area right here, I get 1.09. I'm going to do it again. 3.6 squared divided by 10.6. And I'm going to get, for this column here, 1.22. 4.52 squared divided by 2.848. And I get 2.41. 3.58 squared divided by 7.42. 1.73. 1.89 squared divided by 6.98. 89. 0.518. 1.11 squared divided by 6.89. 0.179. Now these numbers they vary. Some are bigger than others. What might we say about that largest value? The one that's 2.41.
It was the most unlikely.
It was the most unlike what we expected. We expected 13, and we expected 8.5, and we got 13. What can we say about the lowest value on that list?
The closest.
It's closest to what we expected. We expected almost a little bit under 7, and we got 8. Okay? These numbers have a name. These numbers are called, ran out of space writing it, the contribution, or the contributors, because we are near the end. This is the column that we're going to add up, and this is the column that's going to give us our measurement of unusualness. In my case, I get 109 plus 122 plus 241 plus 173 plus 0.58 plus, and I get a value of 7.147, and I give that number a name. I give that number the name chi-square. Okay, the chi is a Greek letter. It looks like an X, except it's got this extra little dealy bob right there. That is the chi-square value. The formula for chi-square, as given on your formula sheet, is that chi-square is equal to sigma of O minus E squared over E.
My contribution values are 5.5.
Okay, if one of your contribution values was 5.53, that would suggest that that particular color was either really overrepresented or really underrepresented.
I have 14 rounds.
You had 14 browns, and you were probably expecting around 7. So you had nearly the double number of browns. Let's go over to Nate. Nate had an unusually small number of reds. He had 2. Now he's down to 0 because he ate the red ones. Okay, and his red contributor value was 3.83. So it's unusual, but yours was even more unusual. So the contributor values help you hone into where are the problems, where's the unusualness in this pattern. Okay? Again, the chi-square value is a measure of unusualness. Like the z value, like the t value that we've already investigated. Now, to end this exercise, we need one more thing. If step 3 in our 4-step process has been get a test statistic and get a p-value, well, we're halfway there. We have a test statistic. What we don't have is a p-value. How unusual is this outcome? Because when I get an outcome this outrageous or more outrageous, 20% of the time, is this just part of the natural variation that happens? Or is this really unusual? Is this a 1 in 100 or 1 in 1,000 unusual? We need the ability to take the chi-square value that you now calculated and now say, what's the p-value? What's the probability that we get an outcome this extreme? Ready? Assuming H0 is true. Wait, where did we assume H0 was true? There's where the H0 assumption came in. We only could calculate the expected values if we had assumption that the model was a good fit. And these are what we expected. Well, it's time to break out your probability tables, and we are now ready to discuss the last table in your probability tables handout. So would you get your probability tables out? And the first one, it's been the first one staring at you all year. And I'm going to bring my table up on the big screen. Okay? And it's the chi-square table. I can make this a little bit bigger. All right. So the first thing that you're going to notice that the chi-square table, like the t table, has a degrees of freedom column. So we better discuss, to begin with, how do we get the number of degrees of freedom that a situation has? The answer to that question is that the degrees of freedom is equal to the number of categories minus 1. Now, at one point we talked about degrees of freedom as like how much information do you have to have before you have complete information. For example, I set one of my M&Ms to the side. And I tell you, hey, my M&M, it's not yellow, it's not blue, it's not orange, it's not brown, and it's not red. Can you tell me what color my M&M is? If it's not blue, not yellow, not orange, not brown, and not red, it's got to be green. So you can tell me, if I give you 5 pieces of information, that's complete. So the degrees of freedom refers to how much information do I have to give you before you have complete information. Same thing worked in the t situation. Hey, I've got 4 numbers. The average of those numbers is 5. 4 numbers, and the average of the numbers are 5. I tell you the first 3 numbers are 4, 5, and 5. Can you tell me what the 4th number is? Got to be 6. Oh, wait. So when I tell you 3 out of the 4 pieces of information, I've actually given you everything you need. Everything about that data set. When we were doing t-distributions, the degrees of freedom was 1 minus the sample size. Because that gave you, once I gave you n minus 1 pieces of information, you can calculate what the next one is. Once I tell you 5 pieces of information about that M&M, you actually know what that M&M is. So the number of categories minus 1 is our degrees of freedom. So in this case, we have 5 degrees of freedom. Now the rest of the reading of the chi-square table is going to be like the t-table. The chi-square distribution is not normal, but rather is right skewed. And for every chi-square value, by the way, the chi-square values are always positive. For every chi-square value, this table will give you the probability of being in that upper part of the tail. So, if I have 5 degrees of freedom, and I have a chi-square value of 8.12, that means in that tail, now you go up to the top of the chart, is 15% of the distribution. Now your chi-squared value is not going to, it's unlikely that it's going to be exactly one of these values. For example, what was my chi-square value? 7.14? 7.14 falls in that range. So what's the probability that I would get that extremely strange distribution of M&Ms? Somewhere between 20 and 25%. My p-value is somewhere between 20 and 25%. How would we interpret that? That's not very unusual. It's greater than our typical alpha value of 0.05. It would lead us to fail to reject the null hypothesis. We have insufficient evidence that my M&Ms are very strange. Okay. We are going to continue this discussion tomorrow. All right?
Okay.